Okay, everybody, this is Chapter 11, Section 1. We're getting into working with surface area and volume in this particular chapter. And this first one kind of defines what a polyhedron is, which is really just a many-sided figure, but it could be three-dimensional. So that's kind of what you're seeing there. We're really going to work with some basic ones. So surface area is really kind of outside part of the polyhedron. In this case, you're going to learn about faces. All the area of the face is kind of added together, but we have a bunch of formulas for this. So you got to make sure that you really kind of are working with the formulas, getting to know them, got to memorize them. You got some other ones that kind of come into play. We're going to go back to regular polygons and find the area of a regular polygon. So that was from Chapter 10. We're also going to have to find the area of circles and the circumference of circles, and we're going to do some other stuff. So just a lot of stuff kind of goes into some of these problems. They can get kind of complex. I'm going to do it kind of step by step too. So there'll be a lot of extra work, but I just want to make sure you all understand the steps in this chapter. Okay. So the first definition we have is for a polyhedron. And it's a three-dimensional figure whose faces are polygons. So remember, polygons could be anywhere from a triangle up to a 20-sided figure. We're not really going to get that radical on it. Okay. The second definition is a face, and a face is a polygon that is a side of a polyhedron. Okay. I think your notes are a little bit different than mine. You actually have a place to write that. Okay, but a face is just a polygon. Like I said, it could be from a triangle to a 20-sided figure. Okay, an edge is where two faces meet as a segment. Okay. So I've got, a whole bunch of edges around here. I got the edge that this one's pointing to. This is an edge. This is an edge. That's an edge. You got a whole bunch of them around there. Okay. And the last one is a vertex, is a point. Where two or more edges meet. Okay. Sorry about my writing. Trying to squish it. That's bad anyway, you guys know that. Okay, so you got to know what an edge is. You got to know what a vertex is. You got to know, you know what a polygon is, but it creates these three-dimensional figures called polyhedrons. Okay. We got to determine, taking the definition of these different figures that we got. It's a polygon, so it has to be made up of a bunch of polygons. You could have different polygons making up a polyhedron. Okay, so a polygon would be like that's a triangular prism, and it's made up of a couple of triangles and then a couple of rectangles making up its faces. So yes, this is a polyhedron. Okay. In B, a circle is not a polygon. Okay, it's a figure, but it's not a polygon. It doesn't have many sides. Okay, so this would be a no. But kind of an interesting thing, we'll kind of talk about this later. This is called a cylinder, and if you think of it like a can of soup, and if you go and buy a can of soup and you take the label and just kind of slice it down its length and peel it off of the can of soup, you get a rectangle. So we're going to kind of use that when we talk about cylinders. a little bit. This is C is a sphere, and it does not have many sides, so that's a no. And then this is a pyramid. So this pyramid's made up of a base. It looks like it's square. It could be rectangular, and then 4 triangles. So those are all polygons. So this is a yes. It's a polyhedron. Okay. All right. We're going to run through a couple of different things too. We have some definitions here: regular and convex. You kind of should know these already. We've used these before, but regular is that the polyhedron has congruent faces and identical vertices. Okay. So really the important thing is all the faces, whatever they might be. They might all be triangles. They all might be rectangles, squares, whatever. Hexagons, pentagons. All the faces are congruent. Okay. Convex, kind of the opposite of that. Big old definition here. A polyhedron is said to be convex if its surface does not intersect itself and the line segment joining any 2 points of the polyhedron is contained in the interior of the surface. So they give you kind of an example here of what's convex. Okay, so it's this kind of ugly looking thing over there. Okay. So this last piece, like if I drew a line between, this point here and that point there, or this point and that point, that would be the interior of the surface, something like that. Okay. We don't really get into that too much. There's just some terms that go with it. Another one's a cross section. Cross section is the intersection of a solid and a plane. So if you remember way back in August when we talked about planes, it's just a flat surface. Think of a piece of paper, and I'm going to intersect some 3-dimensional figure, whatever it might be, and I want to think of what that creates, what figure it creates when I do that. So for a couple of these down here examples, pretty easy one here. Let's just assume one that this is this 3-dimensional figure is a cube, but I intersect it with the plane. What kind of figure do I get in that cross section? So it's like I'm taking a slice out of that, and I believe that if I call it a cube, it would be a square. Remember, a cube, all the side lengths are the same. It could be a rectangular prism, and so if I took a cross section from a rectangular prism, I'd probably get a rectangle. Okay, this one's kind of a little bit difficult. This plane is actually intersecting the corner of this cube. I'll call that a cube again. Intersecting the corner at kind of an angle. And so this one's pretty hard to see. It's not a very good picture, but I should get a triangle from my cross section there. Okay. And then this one, this is a sphere, and I slice it with a plane, and I believe that I would get a circle from that cross section. Okay, so that we don't really do a whole bunch with the first two, but C actually comes up a little bit later in the chapter. Okay. All right, we're just going to fill this chart in. The first two are really what you're going to have to do. But then this formula down here at the bottom, Euhler's theorem, kind of a famous theorem, and we'll use it a little bit. It'll be on your test, so you just want to make sure you got it down. It's not really that hard. But in this chart, just kind of nice to have, but not a real big deal. But let's just fill this in really fast and have it, and then really the first two, the regular tetrahedron on top and the cube on the bottom, are what we're really going to have. So it's got 4 faces, it'll have 4 vertices, that creates 6 edges. For a cube, I have 6 faces, I'll have 8 edges, and that will get me 12 edges. Okay, I think 8 vertices. Okay, for a regular octahedron, I have 8 faces. I'll have 6 vertices. That will get me 12 edges. For a regular dodecahedron is 12 sides. Put that down so we remember. I'll have 12 sides. It'll give me 20 vertices and 30 edges. For a regular icosahedron, I'm going to have 20 faces. I'll have 12 vertices, and I'll get 30 edges. Okay. All right. So using Euler's theorem, it's number of faces plus the number of vertices equals the number of edges plus 2. So we're going to give you these A and B here, examples here. I'm just going to take these values and plug it into what I have. This 2 is a constant. It deals the relationship between the number of edges adding up with vertices. So I'm going to take faces was 5. Vertices is what they want me to find. Edges, they give me 9, and I'm adding this constant 2. So I'm going to get 5 plus B equals 11. I'm going to subtract 5 from both sides. I get a number of vertices is 6. Okay. So once you try B on your own, see how you do, and then I'll put the solution up. So the number of faces is 20. The vertices they give me this time is 12. They don't give me edges, and it's plus 2. Okay, so 32 equals edges plus 2. I'm going to subtract 2 from both sides. I get the number of edges is 30. Okay. All right. So we got this soccer ball thing down here, and we're going to use some kind of common sense here. We haven't seen a soccer ball like that since forever. I think that's the kind of soccer ball I used to play with when I was a kid. Now they're kind of more fancy than that. But anyways, a regular old soccer ball was made up of 20 regular hexagons. That's the white panels of the ball. And then it's made up of 12 regular pentagons. That's the black. So if you think of it, how many vertices does it have? Well, I can't match on technically a pentagon onto a hexagon, but I can make a hexagon relate onto pentagons. So I have 12 pentagons. Each one of them has 5 vertices. So that would get me 60 vertices. So if I was sewing this thing up, there would be basically 60 corners. Okay. And that's where, you know, all these kind of come together right there. That's a vertice or vertex in that case. Okay, so that's section 1. A lot of information here that really isn't necessary as we go through the rest of the chapter, just getting kind of introduced to 3-dimensional figures. Okay.